is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, and welcome. This is Mark D'Antonio, and you are tuned into KGRARadio.com and listening to Sky Tour Radio here this Sunday night, January 19th. I have with me, of course, Amanda. How are you, Amanda?
I'm well, thank you. How are you?
I am fine, and unfortunately, Daryl can't be with us tonight. He's under the weather a little bit, but he will be joining us again next week, and of course, with all of our Sky Tour live streams coming up. We have a lot to talk about there, too, Amanda. A lot has happened with Sky Tour live stream in the last couple of days.
Yes, definitely. And just want to say, feel better, Daryl. I'm sure he's listening in bed, hopefully curled up.
Yes, I'm sure he's listening, and he's smiling and saying, "Oh, everything's better with Amanda." That's his line. I think is really a good line. So here on Sky Tour Radio, we are an astronomy show. We typically talk about astronomical things, and we're not going to deviate from that tonight. But we will be talking about a few very interesting notables. Those are things that are happening now in the news that we're aware of. And you might have heard of these things, but we'll be getting to them. First, a few announcements. We talk about Sky Tour Livestream. What's that? Well, it's a clear night journey into the wonders of the deep sky, all courtesy of research-grade, high-quality telescopes here at the John Zach Memorial Observatory in picturesque northwestern Connecticut. We can see stellar birthplaces. We see the remnants of dead and dying stars. We view these glittering jewel boxes of stars and rich clusters. You can stare at them for hours and just like, wow, these are beautiful, and they're many light years away. You're seeing their light, in some cases, thousands of years ago when it was first emitted from those stars. That's the vastness of space speaking to you. Now, you can also find yourself right in the middle of a request where you might decide you want to see something. So you can pipe up. Amanda is usually the co-host with us, along with Daryl. And we will take your requests. And if the telescope can see an object, we might go to your object and then talk about your object. I wish we could name your object for you, but it's been already named by guys like Charles Messier and a bunch of other people that created catalogs of these objects in the sky. But I will say this. The folks that listen and watch Sky Tour live stream are sometimes the same people that listen to Sky Tour Radio here on KGRA Radio. And we know from experience, Amanda knows this too, I think, the KGRA listeners are really the greatest audience. And I will say this, the most knowledgeable audience on the planet. I think
I did know that.
You did. Yes, you did. You've said that a few times yourself. You've made that observation. And you can't help but notice these things, One more announcement I wanted to make. The book, The Populated Universe, the book that I wrote, it's about exoplanets and extraterrestrial life. It's available now in 3 formats on Amazon, for 3 formats for 3 different budgets. If you want an ebook, you can pick it up for $10. If you want a printed book in black and white, you can pick up the 6x9 format for $20. If you want the full color 8x10, you can grab that for $38.50 on Amazon. It's jam-packed. I didn't realize how much stuff went into this book. But if you listen to how I talk on Sky Tour Radio, you know that sometimes one sentence has a whole bunch of things in it that, beg for further explanation. So what I did was I actually chose to actually make those explanations in the book. So that's what made it a book that's well over 300 pages and packed full of really cool information and observations. But pick it up. It's on Amazon. And if you want to leave us a comment, you can talk to us at our mail. We have an email now. We've had it for a while now. It's called Sky Tour Radio, SKYTOUR Radio @KGRARadio.com. Yeah, and it's a wonderful place. We have emails that we get from people fairly routinely. It's pretty cool. So tonight on Sky Tour Radio, we're going to talk about dust grains from before our time, habitable worlds with tests, and a star possibly about to explode. Now, how's that for interesting lead in here, Amanda? What do you think?
It's quite the catch.
It's quite the catch, isn't it?
Yeah.
So, what are we talking about when we talk about grains from before our time? You might have read a news story or seen a news story about the fact that astronomers have found a meteorite that has grains in it that predate our solar system's existence. Now, I think that's a pretty interesting find, considering that the universe that we know, the solar system with the sun and the planets, are 4.6 billion years old. So there was a meteor that struck the Earth way back in 1969, actually, or 67. I'll tell you in a sec. The truth, what it is, I forget. And Carl Sagan, my favorite astronomer, would always say, we are made of star stuff. And I used to love that line, star stuff. And certainly we are. We're made of the material that was, here in the solar nebula when the sun formed and the planets formed. And of course, we came from all that. So it's true. We are made of star stuff. But now, astronomers found this pre-solar, we call it pre-solar, before the sun, pre-solar grains in a meteor. And they're 7 billion years old. So really, the dust is 2.6 billion years older than our solar system. Now, first of all, I'll answer a question that some of you are already asking. And that is, how do they know that? How do you date something like that? Well, when a dust grain is made in interstellar space, and we'll talk about that, it's composed of atoms. The atoms can be changed from the continuous bombardment by cosmic rays. In this case, a mineral called silicon carbide showed that some of its atoms of silicon and carbon had been transformed into other atoms like helium and neon. And so being, just counting how many of those have been transformed will tell you the age of the material. And it's a pretty well understood process, and the timing is also pretty well understood on how many atoms will deteriorate or decay over a certain amount of time from this pelting by cosmic rays. And this is something that we can use to get an age on these very, very special grains. Now, here's the interesting part. These ancient grains that predated our solar system came from a meteorite that fell in Australia in 1969. It's called the Murchison meteorite. I've talked about it all over the world in talks that I've done. The Murchison meteorite is one that actually had amino acids in it. Yet it had, in other words, organic material. So for the panspermia crowd out there saying, hey, life was delivered to the planet, technically you're not wrong. You're only wrong about the fact that we can't say for sure that it was life that was delivered, but it was the building blocks of life that were delivered for sure. And that's what made the Murchison famous, was the amino acids. So now it is famous once again, and it has renewed fame because of these grains that were found. Now you ask, well, how can it contain such grains? Wasn't everything made from elementary components here in our solar nebula when we all first formed? Well, yeah, and no. The sun is made of other star stuff, and there was debris in our solar system, debris that contained grains from previous stellar events by other stars. So it stands to reason that some of that debris that was here in our solar nebula came from a long distance away and from stars that had long since died. So in a sense, there isn't too much of an issue with it. The fact that we found them, though, is really kind of cool, because up to this point, the oldest rocks we had were just about 4 billion years old here on this planet. Well, now we have some that are 7 billion years old, and they're not even from the Earth. They came from space. I think that's pretty cool. Now, we'll talk about...
There were no new elements found at that time, though. Were there?
No, there were no new elements.
Okay.
And still no new elements. In fact, the element that decayed into the silicon, when the silicon and carbon atoms decayed into helium and neon, is something called silicon carbide, which is well known. It's a compound, a mineral called silicon carbide. and the rate of decay and the rate of transformation of the atoms based on cosmic ray bombardment is somewhat well known, and so that's what they use to age it. I think it's a very, very interesting find, especially since it's been sitting in a cabinet since 1969. And after they found the amino acids, they put it very carefully back into the cabinet. And only upon a recent research expedition did they discover these pre-solar grains. So that shows you that even the older samples are really, giving us a tremendous motherlode of information. I think that's pretty cool. Now, we haven't even gotten to our exoplanet roundup yet, Amanda. So we have that too. Are you familiar with the satellite that's out there now that's replaced Kepler?
No.
Okay, it's called TESS.
I've heard of TESS. I didn't realize it replaced it, but I've heard of TESS, yeah.
Yeah, TESS is the Transiting Exoplanet Survey Satellite. It's a successor of sorts to Kepler. It was launched in April of 2018 on one of SpaceX's Falcon boosters. And TESS has 4 cameras on it that each have a 24 by 24 degree field. Now, that means kind of a little bit of a wide angle field. If you can imagine a wide angle camera, imagine 4 of those all looking up in the sky at once. If you add the fields next to each other in one long strip, you get a field that's 24 degrees wide by 96 degrees long. And that's what TESS sees, 24 cameras times 4 of them, all in a linear path. And you actually see that much sky all at the same time. That's different from Kepler. Okay, now TESS is also looking for transits like Kepler did, and the re-engineered K2 mission of Kepler. All right, and the difference is TESS is looking at thousands of stars at a time. Kepler only looked at one at a time. So it's a step up in technology and processing. Requires a lot of processing power. And so when we say it's looking for transits like Kepler did, what those are, these transits are the imperceptibly small diminishing of the light from a star as a planet crosses in front of it, as seen from our perspective. So if you're looking at a star system far away and it has planets, if they're on an angle that has the plane of their system kind of flat to us, edge on, then we might see planets cross in front of the star. And if we do, the star's light will dim a little because these planets are blocking the star's light for a period of time. And this is the kind of thing that TESS is looking for. And there are a lot of high hopes for TESS because NASA estimates that this satellite can locate up to 20,000 planets potentially. And that's based on the current statistics of what it's looking at, how many planets we found around these types of stars to date. And TESS has just gotten started. There are many stars we think that could have planets, but we have, thus far been unable to find them because we don't have the ability to look in these vast tracts of sky like TESS can do. Kepler was a needle. It was like looking at through a needle, through a straw. And Kepler's like looking through a giant cone. So it's a very different thing. So until the successful deployment of TESS, we hadn't any chance of looking and getting a coarse estimate of how many other planets are out there, potentially like the Earth. Now, the question is, why can TESS find more planets than Kepler? Now, yes, it has a wide-angle field that's looking at thousands of stars. That's certainly one thing. But there's more to it, and it takes a little deeper look, and we're going to look a little deeper here. If you consider how TESS operates, TESS is looking more in what we call red wavelengths, and those are wavelengths of light that are measured in what we call nanometers. Nanometers are billionths of a meter. So the length of a light wave is very small. And Kepler, looked in the region between 400 and 900 nanometers. I know that doesn't mean much to you, but I'll tell you more about that in a minute. Okay, so when Kepler saw light that's 400 billionths to 900 billionths of a meter long, that's the range in which it could see. Its sensors could see that. Now, light comes in different lengths, depending on its energy. Lower energy light is longer and lazier, and it's also redder light. Okay. High energy light is very energetic, and it's also shorter wavelengths. See, I'm talking staccato. That's how it works. So it's short and sassy, but it's also blue. So higher energies are blue, lower energies are red. Now, you might remember when we talked about the spectrum, we talked about the higher energy lights are blue, and the ones that you can't see are far off the end of the blue in our spectrum, and they're called ultraviolet. Those are the things that sunburn you at the beach. Yeah. And there's different kinds of ultraviolet, and then there's even higher energy, which goes into gamma rays and so forth, which is very dangerous for us. And if you come back into the blue a little bit and you start entering the range where our eyes can see, then you reach the visible range. And that goes on and on and on until somewhere in the red. And then there's a point at which you can't see the redder light anymore. Your eyes can't see it. And now it's light we can't see. It's infrared light. Now, infrared is also heat. So it's kind of weird when you tell people, oh, yes, infrared energy, light is, heat is light. People go, what? It's a hard thing to understand sometimes. But it has to do with just electromagnetic energy at different wavelengths and different energy levels. That's what it is. So Kepler then, in this understanding, sees in the short and sassy range a little bit, which is the blue, and it sees through the visible range, all right? And it only looks a little bit into the long and lazy range of red light. Kepler's looking at stars, remember, so when it looks at the stars, it sees many wavelengths or colors, right? And those colors are defined, as Amanda knows, and could tell you with our spectral classes, which Amanda can rattle off right now. Go right ahead. They correspond to the colors. Go ahead. Tell everybody you know it.
O, B, A, F, G, K, M.
Absolutely right.
Yay.
And as she will finish saying, it goes from, and I'll say it for you, it goes from the hottest and bluest to the coolest and reddest. Okay? And so Kepler's looking at stars, and it's looking at these stars with these different colors or wavelengths. But it stops seeing the stars beyond 900 meters. It can't nanometers. It can't see beyond 900 nanometers. And that's right about the end of the visible light spectrum, which our eyes can see. So it's limited like our eye in the same sort of way. Now, Tess, on the other hand, has a different spectral response. In other words, it can see differently. It sees not so much in the blue. It sees from 580 nanometers, which is out into the blue and the ultraviolet, all the way out into the red, and then beyond into the infrared at 1100 nanometers. So it's sort of a slit, and the window's slid a little. Tess is seeing more into the redder side of the spectrum. Now, why is that? Well, it sees some of the blue, but it sees way more of the red. Now, why is it? Because Tess is looking at mostly these faint red M-type stars. Amanda just told you the spectral classes O, B, A, F, G, K, M. M is the coolest, faintest, and reddest. Well, that's where Tess is looking. Tess is looking at these stars because these are the stars that we think have more planets around them than any other stellar type in the universe. And so far, we haven't been disappointed. Kepler's shown that we haven't been disappointed. Most of the habitable worlds that we've found are around M stars. All right? We'll talk about that later. So, Tess is an amazing satellite, all right? And when it's looking past the red and into the infrared, it's looking for what we call the excess IR, the excess infrared. In other words, heat that is emanated, that can be seen. Since heat is light, we can see the heat of this, the light of this heat from a long, long way, many light years away. We can see that as long as it's bright enough, and as long as Tess is sensors are sensitive enough to see it. Okay, so because
did Tess go where Kepler went? Like, was it sent to the same location?
No, Tess is not in the same location. Actually, I'll have to look up the orbit of Tess, but it's not in the same place as Kepler.
Okay.
Yeah.
Is Kepler still going?
No, Kepler has unfortunately exhausted the last of its onboard fuel that it did use, and it is no longer functional. I mean, if they could refuel it, I'm sure we could still use it. You know, fix one of those, those little wheels, those gyrating wheels that help keep it pointing in a certain direction, and it can be brought, good as new. And when we have a space force that can actually go out to places like where Kepler's located, then we'll be able to do that. But right now, they're one shots. If they die, they die. We can't fix them. So if we consider, if we think about TESS, the deck is stacked in favor of TESS for finding planets. So when I said 20,000 possible planets, well, Kepler only found about 4,000 overall, and TESS is going to find more than 4 times that, maybe. And so the way it's going to do that, though, is because of its sensors. Its sensors are tuned to seeing stars that are fainter and have redder light. M stars, are also only sometimes about a tenth of the size of the sun. And so when a planet crosses in front of those, the signal, the transit that we see is going to be bigger and more noticeable because a star is smaller, and a planet relatively is a lot bigger compared to a lot bigger than, say, it would be crossing in front of a G-type star like our sun. Because the sun's so much bigger. A star that's only 1/100th of the size of the sun, well, a planet passing in front of it's going to make a noticeable impact. Noticeable transit line. And so that's why the deck is stacked. That's one reason. Furthermore, this bandpass that TESS is using from that 580 to 1100 nanometers, that's uniquely suited to these M-type cool stars. And we told you they're the most numerous star in the universe, and they probably have the most planets as well. So TESS has bagged big game. And, it's the first time that we found something like this. And that big game is that TESS has found 3 planets around a nearby star called, the star is called TOI 700. And TOI means TESS Object of Interest. How cute. All right. But it found 3 planets around TOI 700. And they're labeled B, C, and D, little b, little c, and little d. And that's the same as like Kepler Object of Interest, KOI. All right. But for TESS, so TOI. Now, this star is a low temperature red dwarf, and it's 101.5, if you want the fractions, light years away. And these planets orbit this star. It's an M2 and then Roman numeral 5. If you remember, the M2 was the spectral class, and the 5, the Roman numeral 5, that's a V, means that it's a normal, quote-unquote, dwarf. It's fusing hydrogen to helium like most stars. And so it's in this line we call the main sequence. It's one of the main, it's like one of the main stars in the universe. It's something that's very common in the universe. And it'll continue to do this for hundreds of billions of years, maybe longer. So it's only less than half of the mass of the sun and less than half of the radius of the sun. And its age is around 1.5 billion years. So it's a cool red dwarf. Now, the first planet is planet B. All right. It orbits 0.06 astronomical units from the star. Okay, it's very, very close. At this distance, it only takes 10 days to orbit the star. Okay, so that's a short year. All right. Mercury's year is 88 days. Okay, so obviously it's a lot farther away. And it's about the same mass as the Earth, this one that's really close. And its radius is about the same as the Earth. However, it's too close to this star, even this cool red dwarf, to be in its habitable zone. But there's a second planet, and that's labeled little c, and that's 0.09 astronomical units from the star. And it takes 16 days to go through its year. All right. And it's 7.5 times the Earth's mass and 2.6 times the radius of the Earth. So most likely in what we've found, this sort of indicates that we're looking at something that might be more like a small Neptune. So it's probably a gas giant, and it's also just a little bit too close to the star to be in the habitable zone. So these first 2 planets, B and C, are right out. But you know what? There is a third one. a third planet, and that one's labeled Little D. Okay? And that's the planet that we're going to talk about right after we get back from this break. You like that, Amanda? You like how I did that?
Yes, because I had a question too, and I was going to save it for after break.
Oh, see, well, guys, we'll be right back after this break. Amanda and I here on SkyTour Radio will welcome you back with open arms or open mics. I'm not sure what it is, but hey, we'll be right here waiting for you. Don't go away.
Why is it we're not very good with our health regimen until it's too late? We don't put oil in the car until the engine blows up. When the body's out of balance, your health is not so good. Give your body some love. Log on to GetTheT.com. That's GetTheT.com. Try our Life Change Tea, which cleanses you from harmful intruders. A clean colon is one of the ways to bring the body in balance. We also carry organic supplements to help you get where you need to go. So do your body a favor. Log on to GetTheT.com. That's GetTheT.com. You can even visit our sales page to save some dough. Does anybody call money dough anymore? Anyway, if you're looking for short, helpful health tips, go to YouTube and punch in Health Matters Now. That's Health Matters Now. So, log on to GetTheT.com, shop, get balanced, then learn some cool tips at Health Matters Now. You'll be glad you did. That's GetTheT.com.
You can tug all day long on a carpet that's been glued to the floor. Then you hurt. There are many strong glues out there. Let's see, there's liquid nails and Gorilla Glue. You ever try to remove 3M 5200? That adhesive is strong. Then there's bathroom caulk, silicone rubber, adhesive tape, super glue, flex tape, and stickers. Graffiti. Scientists have come up with glues that stay stuck and can't be removed. Until now. Until Handyman Formula by DeBond. That's right. 95% of adhesives become unstuck when you spray Handyman Formula directly on them. Just spray, wait a few minutes, and remove. It's amazing. Most adhesives become unstuck when you use Handyman Formula. Visit DeBondCorporation.com or MCMaster.com. Call 561-575-4200. This stuff really works. Handyman Formula by DeBond, a great Christmas gift.
Hey, is that a new music app?
Yeah, check it out. Surfer Music Discovery. It links to thousands of online stations, but the twist is you see the song names and artists that are now playing live.
That's different. No guessing. Looks like a waterfall of music.
So many formats. Rock, oldies, country, R&B, jazz, and a whole lot more.
How's that spelled?
Surfer. S-U-R-F-R.
Is it expensive?
It's free. No need to sign up or sign in.
Get the Surfer Music app free from Google Play or the App Store. Are you intrigued by Paranormal Talk Radio? You'll love the new Paranormal Radio app from TalkStream Live. You'll find a great selection of talk shows covering UFOs, ghosts, strange phenomena, and much more. Download the Paranormal Radio app now and start listening to the very best in paranormal talk entertainment, including the network you're listening to right now. The Paranormal Radio app, free in Google Play and the iOS App Store.
More ways for you to make contact. Live Discord chat rooms, live talk radio, live video cast, toll-free HD phones, and coming this year, live streaming TV, giving you more ways to make contact. Your KGRAradio.com.
Hey there, welcome back to SkyTour Radio. This is Mark D'Antonio with Amanda Curran, and before the break, we were talking about the test discovery around TOI 700, Test Object of Interest 700. It's a star, and it's really important because, not because it found 3 planets. I mean, that's always important. And we talked about the first 2, but it's also important because the last planet test found, D, little d. There was B, C, we talked about, and now D. Well, it's 0.16 astronomical units from this star. And again, it's a small M-class star. And it only takes 37 days to orbit the star. Now, it's literally it's like 1.19 times the Earth mass. It's very close to Earth's mass and also very close to Earth's diameter. The most important observation, though, besides being nearly Earth-sized, is that it's in the habitable zone for this particular star, and that the 0.16 astronomical unit distance is smack dab in the habitable zone of this star. And we know that habitable zone means you can have liquid water. Now, this star is an M2, Roman numeral 5, as we said. And if it's a rocky planet and it has an atmosphere, then perhaps life could form here. Now, that's really important. It's the first Earth-sized planet that is in the habitable zone that Tess has found. And it's a really, really important find. It's one of those finds that I don't think, I don't know, it's actually pretty hard to, it's pretty hard to beat this one, I'll tell you. And one really favorable characteristic about this particular star system is that it's pretty stable. There's no flares from this red dwarf star, and all the time they've been studying it. Usually red dwarf stars will have a flare propensity. They'll actually have flares that will shoot off from time to time. And these flares can be heavy in the ultraviolet, causing, sterilizing radiation to bathe any planets in that system, perhaps. But this particular star is rather quiescent. There's no problems with the star. So maybe this is a good one. This is really what we would call an exceptional candidate, a robust chance that there's potential for life here. And when you hear an astronomer, and other astronomers have used this, not just me, they've called it a robust candidate for life. That's pretty much going out on the edge to say that, but they have. So this particular planet, of course, it has to have an atmosphere. We can't see it. However, it is close enough to study. It is, okay? We'll be able to see, with the James Webb telescope, we'll be able to see whether this has an atmosphere or not, potentially. And it's something that I think is important, really is important. We need to have, we need to find these worlds. So now, speaking of habitable worlds, where do we sit with habitable worlds? Now I'm going to go into that question in a minute, but I do want to just check with Amanda because I want to find out. I don't have the chat up right now, and I can't see if we have any questions. So I'd like to know, Amanda, if we do, and I'd like to tackle those now before we go into habitability.
We do have a few questions. We just have another one coming in now. Our first one was from Carol.
Okay.
And she wants to know, how small of a period of transit time can we observe? I guess using TESS.
Well, the period of... Yeah, it does. I know what she's trying to ask, sure. The transit period can be anything from a few hours to a few days, and possibly even longer. It depends how far the planet is from the star. If it's very close to the star, then the transit period could occur in just a few hours if the planet is circling the star very close. There are planets that do. I don't know the transit interval for these planets, but, I mean, we could work it out, knowing how far away they are and their mass and the type of star. We could probably figure out their orbital velocity, figure out the diameter of the star, and then figure out what the transit curve should look like. But I think we're probably looking at a transit curve of perhaps for the outermost one, the Earth-like one, maybe the transit curve is going to be in terms of, say, a day or maybe just a part of a day. It goes around its star, once in just a few days, right? So we're talking about the fact that this thing can actually be caught in a transit. So I just think that these are outstanding. At the distance this thing is, I think it's really important to be able to, look for more of this 37-day orbit of the star, trying to get more data on it. Let the James Webb see it when it goes up. That'll be very important. So the transit time that you can measure is variable, from just a few hours to actually probably could measure even smaller than that. But to a long period of time too. If a planet is far away, imagine if you saw Jupiter passing in front of a star, our star, from some other star. It's going to take quite a while to cross in front of our star. You know how long it takes to pass through our sky. You see it all winter long, all summer long, and sometimes you can see Jupiter in the sky. You know, it moves very slowly. Well, it's going to pass in front of that star fairly quick because the star is only a point of light from the distance, but so is Jupiter. So, you know, it'll yeah.
Okay, so what did they do? They just sent Tess out into the wilderness, and then what? They found something of interest, so they just stayed there for as long as it took for all the planets to orbit?
No. What happens is Tess is scanning the sky, all right, and it's actually.
Is it still moving?
Huh?
Is it still moving?
Yeah, it's in a highly elliptical orbit around the Earth. Okay, all right. It basically will be about as far away as the moon, and be a little bit closer than the moon. It's in a very elliptical orbit. All right, and so it orbits Earth a couple times for every time the moon goes around the Earth. So I think that is probably why Tess can be just looking at the same place for a long period of time, because there's nothing to block it. Okay, we got a nice fine elliptical orbit out there. You know, elliptical.
But is it watching that area the whole time it's orbiting, or does it only catch it? You know, like if it's like, say it goes around twice every time the moon does, like does it only have like a small little chance at a certain area to see? Do you know what I mean? I don't know how to explain it.
I think you're asking, is it looking at the same place all the time? And
well, can it be? Obviously, it's not always, but I mean,
it can be. It can be. It's designed to, and it has to, because it has to be able to see repeat transits for planets that might be, you know, closer to the star.
Yeah, that's what I'm trying to get at. Like, it's not like once it finds something of interest, like this B, C, and D.
Yeah.
Like it can't just like stop and just check it out for like a year or two. You know what I mean? Like.
Yeah, but don't forget, Tess is looking at a field of view that's 24 degrees wide. Okay, in other words, make a fist and hold it out at arm's length, and then open up your thumb and little finger and stick them out. Okay, that's just about 20 degrees. And Tess is looking at a field wider than that. And then as far as when you put that arm down toward the horizon and raise it all the way up over your head, that's the swath it's looking at all the time, continuously. So it sees that all the time. So anywhere in there, if a star is undergoing a transit, it's going to catch it. So it's looking at thousands of stars at a time. You see? Kepler wasn't.
But as it orbits, does that picture not change?
No.
Like the location and the...
No, it doesn't, because the stars are so far away. It's looking at... If it was looking at, say, Jupiter or Uranus or Neptune, yes, the picture might change a little. Okay? But it's not. It's looking at planets that are light years away around other stars. So the planets don't even perceptibly move as far as Tess is concerned. Do you see?
Okay, what is it orbiting, if that makes sense?
It does. Tess is in orbit around the Earth.
Around the Earth, but the Earth never blocks our view of the sky, of the section it's looking in.
That's correct. Tess is not. I'm not sure whether Tess has to worry about lights from the Earth or any kind of reflectivity off the moon or something like that. But yeah, I don't know those particulars about the Tess orbit. But that's certainly something we could find out. But those are all good questions, because
I'm just thinking, if it orbits Earth, it doesn't. I can't wrap my head around how far it can be out from us. Like, it doesn't seem like it's really that deep into space.
Well, it's out.
If it's still orbiting us.
No, it's out about the distance of the moon when it's furthest from us. Okay, and remember that the moon is like a 3-day trip, with our rockets. So I mean, moving pretty fast. So it's actually pretty, it's pretty good distance away, but it's not orbiting close to the Earth. When it's closest to the Earth, it's still 108,000 kilometers away from us. All right, and that's still quite a distance away, considering that most satellites are not anywhere near that orbit. Around the Earth. You know what I mean? So, we're looking at a very big gap. There's not going to be anything blocking it. Does that help you or no?
It does. It's a big concept.
Well, it is, and I'm trying to think of another way to phrase it for you to try and help you, because if you're having trouble with it, somebody else will be too. For those that think in miles, I just want to say this: the nearest that TESS gets to us as it's orbiting the Earth is 67,000 miles. Okay, and the geosynchronous satellites are out around 22,000. So TESS never gets closer than 3 times their distance. All right. So we're talking about a very large elliptical orbit. So Earth is not even very big to TESS, relatively speaking, and the moon is even smaller. And based on these orbits, TESS can always be looking in the same area of space and capture data, and it has been. And it's really actually doing quite a good job so far. It's actually predicted, as I told you, to find 20,000 planets, but it's already found an Earth-sized planet in the habitable zone. And I don't know if you guys remember this out there. The KGRA listeners, being as smart as they are, might know this. When we started looking for planets around other stars, one of the things we found was that we could find the Jupiters, but finding Earths was still a distant possibility because they're very small. It wasn't going to be easy to find them. And it turned out that when we went to look for them, there were a lot of error in the ways that we were trying to reduce the data coming from these stars that we were seeing. Well, as it turns out, those days may be gone. It looks like we can now find Earth-sized planets. TESS has found them looking at a 96 by 24 degree field, and Kepler found them as well. And ground-based telescopes have even had some limited success finding Earth-sized planets. So I think that we're talking about a new generation of telescopes here. But even those don't do everything that would be, conducive to finding an Earth-sized planet. We're missing so many. We're missing so many of them. I know we are. However, I will say that this particular world here at TOI 700 is probably a good candidate because it's only 101 light years away. I say only. We're looking at the light from about 100 years ago, right? So, but I think in time, we'll be able to get our technology to the point where we will be able to deduce the components in the atmospheres of some distant planets. All right. Now,
and again, I have really basic questions here. Sorry. How do I phrase this? How are they gathering this information? Is it a whole bunch of people looking in different areas that are being scanned and someone finds an area of interest and then they kind of focus on that? Are there other people looking elsewhere right now while people are studying TOI 700 or whatever?
Oh, absolutely. You've got a lot of exoplanet search programs underway. And to answer your first part of your question, the TESS imagery is vast, and the TESS observations are massive data sets. So certainly there is an artificial intelligent system that goes through the data sets and does some housekeeping stuff reduces the data to the point where it gets rid of any anomalous artifacts created by the system, artifacts created by faulty data. That stuff has to be removed. But then once it culls the bad data, then they can start looking at the light curves to see what happens, see if a star is dimming. Now, here the other problem with it is stars dim naturally. Okay, our featured star tonight is Betelgeuse that we're going to talk about, and Betelgeuse is dimming dramatically. But it's normal for some stars to dim and then get brighter again. They're called variable stars. There's some that are irregular. There's some that are very regular. And there are some that we use as candles to tell distances to distant worlds and distant galaxies because they're so regular. Those are the Cepheid variables. So, and if Daryl was here, he would have said Cepheid variables. He knows. See? So, it's troublesome trying to determine, is this just a star that's variable that we didn't recognize before? All of those things have to be weeded out. Every one of those things have to be put to the test. And we have to try and figure out if one of those can explain the dimming of the star. And sometimes that dimming is explainable. Sometimes it's not, as in Tabby star. Tabby star is a star that's a K-type star. It's a nice orangey star, a little yellowish orange. And it has a planet, the star itself is dimming in very, very strange ways. Sometimes by 20% of its brightness is being dimmed by something. And this led to people saying, oh, it's artificially, it's a sign of intelligence. They're building a Dyson sphere around this star. And Freeman Dyson postulated once that in order for an advanced civilization to capture as much energy as they could from their star, they might encase their star in a gigantic construction to capture every bit of energy from that star. In reality, in the universe, as far as we know, there's no material that could withstand the forces of gravity that would act upon a gigantic sphere trying to enclose an entire star. More than likely, they'll have a swarm of satellites that are gathering energy and beaming it back to the home planet. And that's not a Dyson sphere, that's a Dyson swarm. And maybe that the thought went, this particular star has an intelligence there that is building a Dyson swarm. And over time, we're seeing the dimming of the star because more of their satellites are going into the sky, around their sun, taking its energy. Kind of interesting when you think about the Starlink project with Elon Musk. They launch 60, 100 satellites at a time. It won't be long before there's 14,000 of these up there. We only have to worry about 4,800 satellites right now in the sky. And you add 14,000, and almost every astronomical picture you get may have a streak from a satellite in it. You've seen, Amanda, on SkyTour Livestream. How many shots do we take? And we see a satellite zipping through the page, zipping through the image, right?
I know. I think Daryl feels quite strongly on this, that he thinks the release of all these satellites is really going to ruin the night sky for astronomers.
Yeah, and I know that...
and I see his point. With how many there are here, and we catch them all the time accidentally, I can see it being a problem. It's pretty sad.
I will say this, though. From a professional capacity, what's going to happen at the professional levels is not that they're going to just stop doing astronomy. What they're going to end up doing is calculating windows of opportunity. And they'll have programs that will calculate when the sky will be clear of satellites for however long and over what period of time through the course of a single night. And it's during those windows of opportunity when they will do certain observations that could otherwise get messed up by a satellite going through the view. And that's something that will become a thing. It is now, but it's going to become very important, especially for astronomy on Mauna Kea out there in Hawaii and down at Paranal and Chile and Cerro Tololo down there. That's going to be a very important consideration. The ESA, the European Astronomical Group there, these guys, European Southern Observatory, is going to have to worry about that. And they're all going to have to worry about it. The Chilean folks will, the folks out on Mount Teide in the Canary Islands. We're going to have to worry about that. There's a lot of very, very high-end astronomical observatories all over the world, and they're going to end up having to care about calculating their windows of clarity so they can do this without seeing satellites, especially if they're on the looking at the equator. And it's going to be hard, especially with geostationary satellites. They're going to have to deal with them because they're not going anywhere. They stay in the same spot over the Earth, but if you're taking a time exposure of the stars, they form a trail on your view because they're staying over the spot on the Earth as you rotate out. As the stars rotate out, your telescope's following the stars. Okay, and the stars rotate out. You're rotating out from under the stars. So the satellite is still sitting there over you, except it's being dragged up as the Earth rotates because the stars are passing by, and it's the telescope making them drag out because the telescope is following the stars. It's really weird. And you're right. Satellites do cause problems. I don't know if you remember, we did a Sky Tour live stream where we actually searched for geosynchronous satellites one night, remember? Were you there for that? I think you were.
It sounds vaguely familiar.
Yeah, we would take an exposure, and all of a sudden you'd see 4 dashes in the view. And I'd say, yep, those are 4 telecommunication satellites. And we would purposely go look just for those satellites. And we did. We could find them real easily, So the satellite issue is a problem. Luckily for satellites like TESS, Transiting Exoplanet Survey Satellite, it's not going to have to worry about that. It is literally beyond the haze of satellites that are around our planet as we speak. Never mind the number that are going to be put into orbit later. So it's actually quite a a mess up there, So I don't know. But anyway, let's
actually, Ronald had a question on that. He says, why can't the astronomers or the Science Society just band together and complain about all the space junk? I guess it has too many benefits to outweigh.
Yeah, when you're talking about satellites that do remote sensing of vegetation and examine the soils of distant countries that need desperate help. What are you going to say? We want to take pictures of our night sky, so screw you. We're not going to help you, feed your people. No, that's not going to happen. So we all have to work together on this. It's we're one society on this planet, and boy, that'll become clear as soon as aliens land. Okay, and so that said, I think it's going to be a case where, like I said, for astronomy, we're going to just have to work around this. In a professional sense. I mean, at Hawaii, okay, there's cultural reasons why they're having a problem with the new telescopes going in over there. The Hawaiian, the indigenous Hawaiian population don't want these telescopes in their sacred land. I can't blame them. My mother was part Native American, and I'm familiar with cultural traditions, and I know that things like that are very, very hard to accept. In these cultures. Now, I'm American. I'm not Native American, obviously. I mean, I'm partially, but I understand, and I don't try to make any claims. But the fact of the matter is, there are people that do have problems with it, and you have to respect their feelings and work with them, never against them. That pipeline issue was heartbreaking because it was like, those were sacred lands, for that pipeline they tried to put through there, and it was sacred lands, and they were not listening. It was like they didn't care because money was in the way. So anyway, it was kind of a heavy digression there, I think, wasn't it? Here in this habitable world, we have our own problems, don't we? Do we have any other questions, Amanda?
We do, but we're coming up on a break, so I don't think we're going to be able to get to it quite yet. But
okay,
one coming up about Beetlejuice, and I know that's where we're going next. So
we are indeed. Yeah. We are indeed. All right. Well, we can talk about. Yeah, actually, read the question before the break, and we'll let people think about it.
Ooh, okay. Well, the first part I think I know, but it's a 2-part question.
I love
Is
hearing.
it true? is it true that Betelgeuse might be out already and that we're just seeing the light? And also, if a star is gone, how can we see the physical planet around that star that is burnt out?
Those are excellent questions. Let me, we have about 15 seconds left here. Can you answer that first part of the question? You said you think you know?
I think it's quite possible that Betelgeuse has burnt out and we're still seeing the light.
Okay, we're going to find out why when we get right back from this break. We'll be right back, ladies and gentlemen, and all of you out there in KGRA listener land. Amanda and I will be right back. See you later.
So, you love talk radio? Then you'll love TalkStreamLive.com. TalkStream Live is always on, 24/7 with the best streaming talk shows. Find your favorite talkers and discover some new ones. It's free, readily available online or on mobile with any smartphone or tablet. Finding your favorite talk shows all in one place has gotten a whole lot easier. Just go to TalkStreamLive.com. Be sure to download the free apps from Google Play or the iTunes App Store.
Hi, I'm your host, Smokey Cole Bear. Filling in for Smokey, because after 75 years of...
Only you can prevent wildfires.
Turns out there's much more to say. Nearly 90% of wildfires are caused by us humans being careless, dumping our used barbecue coals willy-nilly. Guess the song was wrong. We did start the fire. That's why I respect Mother Nature and her trees, whether coniferous or new car scented. Brought to you by the U.S. Forest Service, your state forester, and the Ad Council.
Folks, this is very important information. What's to be said about CBD? AncientLifeOil.com. Our CBD is made from hemp and has 0.003 THC, which means this wonderful product won't get you high, no matter what amount you take. What does CBD do for the body? My hands are tied. But you can Google CBD benefits and be astounded. When you're finished reading, you'll want to log on to AncientLifeOil.com. That's AncientLifeOil.com. and purchase. Life is good when you feel good. People are tired of pain. People are asking for non-GMO organic products to help them with, you fill in the blank. Legal in 49 states, and again, our CBD is made from hemp. Ancient Life Oil is about helping people one by one by one. If you wonder how good the product is, the CEO takes it every day without miss. AncientLifeOil.com. That's AncientLifeOil.com. Have a great day.
So, you love talk radio? Then you'll love TalkStreamLive.com. TalkStream Live is always on, 24/7 with the best streaming talk shows. Find your favorite talkers and discover some new ones. It's free, readily available online or on mobile with any smartphone or tablet. Finding your favorite talk shows all in one place has gotten a whole lot easier. Just go to TalkStreamLive.com. Be sure to download the free apps from Google Play or the iTunes App Store.
The new KGRA YouTube channel is now live. Subscribe and be sure to hit the bell to stay up to date on the latest major announcements, alerts on trading topics, exclusive live streams, live video cast, and that's just the beginning. Be the first to know what's coming from the KGRA TV channel in real time. So keep it locked in to your contact for alternative talk radio on the internet. Your KGRAradio.com.
Hey everyone, this is Nick Redfern and you're listening to Sky Tour Radio with Mark D'Antonio on the KGRA network, and so are the Men in Black.
You're listening to the KGRA digital broadcast station.
It's a whole new way of life.
Salt Lake City, Utah. Hudson Valley, New York.
Hey, welcome back to Sky Tour Radio. This is Mark D'Antonio. I'm here with Amanda Curran, and we were talking about something before, actually over the break, before the break, and Amanda was starting to. She said she thinks she knows the answer to a question. And Amanda, are you there right now?
I am.
Yeah, she's back. Yeah. Can you ask that question again that we asked before the break? And I'd like to hear you say what you think is part of the answer.
Okay. The question again was from Ronald. It was a two-part question. And he wants to know, is it true that Betelgeuse might be already out? and that we're just seeing the light. Also, if a star is gone, how can we see the physical planet around the star that is burnt out? So I thought that it could quite possibly be that Betelgeuse is already burnt out. And if so, we might still be seeing the light for 700 years. And it has been dimming lately.
That's correct.
We don't know why yet. I don't think we know why yet.
We don't really know why. We all have all kinds of theories. Now, Betelgeuse is a semi-regular variable. It actually has a variability, and it drops in its brightness. We will be talking about Betelgeuse actually in a little while, but I'll tackle this now with you. So, from what Amanda said, she is correct. Amanda is absolutely correct. Betelgeuse could, in fact, have already. Well, I'll say gone out because that was the phrasing in the question that Ronald asked. All right. But the fact of the matter is, Betelgeuse isn't going to go out quietly. Betelgeuse is only 8 million years old, and it's already burned out or burned through all of its hydrogen. It was originally one of the hottest stars in the universe, one of the hottest and bluest stars. And Amanda knows what that means. We're not going to talk about it now. We're going to talk about it later. But so it's in a point in its evolution called the red giant phase, and it's actually a supergiant. And Betelgeuse is going to end its life in a cataclysmic explosion. Now, at the distance that Betelgeuse is, which Amanda told you, 700 light years, that's right. And she's absolutely correct. The light train coming to us from Betelgeuse is 700 years old. So if Betelgeuse exploded 200 years ago, we wouldn't know it for another 500 years. So that's what's interesting, and we'll get to more of that after. And to the second part of the question.
Hold on a second. Other than the light dimming and eventually ending, would we not see anything else? Would there be no other indication that it went to supernova?
No, well,
like
when
a big release of.
Yeah, when it goes, we'll see it go, and it'll be a star that'll be visible during our daytime. You see the sun in the daytime sky, and it's very bright. Well, Betelgeuse won't be that bright, but it'll be bright enough to be seen in daytime through the blue sky.
Is that after the 700 years?
Well, that's after it goes supernova and that light finally makes it here. That doesn't have to be 700 years from now. That could be tomorrow afternoon.
Okay.
You know, we don't know at what
then
stage
we'd
it's at.
still see the light for another 700 years after that.
If it goes right now,
Yeah.
if Betelgeuse goes right now, its time where Betelgeuse is in space, then 700 years from now, that light will get to us and we'll see it. But if it went 699.9 years ago, then in just a short amount of time, 0.1 years, okay, we're going to actually see, in a couple months, we'll see Betelgeuse go up. You know, we'll see it happen in our night sky. It just takes light that long to travel here. So remember, we always said, looking in space, looking at the universe, you're always looking back in time. And it's always a varied amount of time. When you look at the stars of Orion, you're seeing some of them 700 years ago, some of them 850 years ago, some of them 1,200 years ago. And you know, the Orion Nebula, you're seeing about 1,200 years ago. So, you know, you see things all at a different time scale. We just take it in, oh, look at the universe. Look at all those stars. How beautiful. When I look up at the sky, I say, look at all the different times. We're seeing the universe at all these different times. That's the perplexing thing for me. That's the thing that keeps me up at night. And you know what? It actually does keep me up at night. Do you know I have dreams that I'm trapped in a room and I can't get out until I solve these matters of time in the universe? I mean, what horrible dreams. I mean, and then I've also dreamed that I've been stuck inside of a triangle and I couldn't get out unless I solved all the angles. I mean, what kind of a dream is that? You know?
Wow.
I'm sick, you know? Yeah. You know, I tell you, I get no respect. You know, my mother had to tell you, pork chopper, I'm going to get the dog to play with me. So, honestly, I think that in looking at the stars, we're seeing them at all these different times. We've talked about this before. We see the sun 8 minutes ago. We see the moon just over a second ago. We see each other, you know, a fraction of a nanosecond ago. depending on how close we are. So, I mean, there's a lot of everything is time travel in the universe. Everywhere we look, it's time travel. We see out 13.2 billion light years about in the universe. We can see about that far out. But remember, it had to travel out that far from us. And the light was coming back to us. So it took 13.2 billion years for that light to get to us. Meanwhile, it was still expanding. So it's not 13.2 billion years anymore. It's even farther out. And that gives rise to the overall diameter of the universe of over 90 billion light years, which is just those are all fascinating cosmology topics too to talk about, like what happens, what's the universe made of. I mean, that's going to be one of our shows eventually, is what's the universe made of. And we might have Ket Thorvaldsen as a guest actually for that show, because she's writing a book on astrophysics, and her and I do the New Sciences tour together, and she has some concepts in astrophysics that I think are worth discussing. So I think we'll be doing that at some point. But tonight we've been talking about habitable worlds so far. We're coming to Betelgeuse. Maybe Betelgeuse will explode by the time I actually get to it, Amanda. I mean, it seems like it's taking a sweet time here to get to it. But I can tell you right now. Let's talk about Betelgeuse now. Shall we do that?
Let's.
Okay. Are there any questions that we have to hit first?
There was one. I'm not sure. It's kind of, maybe you can touch on it. It's a little off topic.
Okay.
It was from Galaxy, and he wanted to know.
Entanglement question.
Yes.
I'm just kidding. I knew it was. Okay, go ahead.
Could you explain quantum entanglement, and if it's possible to entangle a particle on one of these planets? I think he was talking about TOI 700.
Okay.
Could we get information from this particle to use in study of the planet? Future possibility.
Okay, to answer that second part first, our science is nowhere near ready to make that make a qualified answer to that. And what information we would get, I can't even speculate at this point. But what is quantum entanglement? Now that I can answer. Okay, quantum entanglement is a really interesting feature, characteristic, if you will. Let's look at electrons in an atom for a minute. And we are getting to Betelgeuse, I promise, guys. I really do. I really promise. When we look at electrons, they have a quality known as spin. It could be spin up or spin down. And if you look at a material and you take a piece of that material and split it, say, and put some in laboratory A, some in laboratory B, and you look at the electrons in one of the atoms, and you compare it to the same atoms in the material in the other room, okay? Let's just generically say that for now. There's more to it than that. But if you look at the electrons around the orbit of the atom and you measure the spin, if it's spin up, you don't have to measure the spin of the electrons in the other room because you already know what they are. They're spin down. All right. And if they do measure it, indeed, they're spin down. So you can't have it be any other way. If it's spin down, then the other ones are spin up. All right. In other words, it's just a characteristic. So in other words, if electrons in room A have characteristic A, then the electrons in room, the second room, I won't say B, but the second room will have characteristic B, guaranteed. Okay. So you have two rooms, and it's always going to be, if you measure A on this electron, it's going to be B on the other one, and you don't even have to measure it. Right? So that means something. What it means is that the electrons, no matter how far apart they are, the atoms, okay, are actually in communication because they know that spin up is happening in this guy's atom over here, so spin down has to be happening over here with me. So how are they communicating? Now, Einstein called it spooky action at a distance, and boy, it is spooky. We don't know. We don't know. And we don't know actually what's really going on there. But we do know that quantum entanglement means that these this quality that we only have to measure one of these electrons to know, because the other one already follows suit. It means that these things are talking to each other, and that's the thing we don't understand. However, I mentioned Ket Thorvaldsen. She's from Norway. Ket has ideas about quantum entanglement that I think would benefit all of you, because she can talk about this from a whole different perspective, because she has a cosmic tapestry that does include a way for all of the atoms to be talking to each other across vast distances. So that means, for instance, that Galaxy's question about quantum entanglement might actually very well have relevance, only just not now, because we don't understand everything yet. So it is a good question, Galaxy, and I want to thank you for that. Now, if we don't have any more, I will actually dare to move on, but it's okay. You can ask if there's one more.
There is, and there's one about Beetlejuice.
Okay.
And it's from Daryl.
Oh, really?
It is. He's listening. He's fighting, staying awake. He's still not feeling well, but he had a question on Beetlejuice.
All right. Well, let's all, first of all KGRA listeners, let's wish Daryl, some health here, because he's feeling under the weather. So let's all just say, yay, rah, rah, Daryl, and right now he's going, oh, like he does.
And we miss him terribly, and he's such a wonderful addition to the show. It's very noticeable when he's not here.
I know, he's an astronomer's astronomer, he's like a guy that knows a lot about astronomy. He's a welcome addition to the show, and I'm glad that you were able to convince him to join us for forevermore here, Amanda. Yeah. So, okay, what's Daryl's question?
He wants to know, is Beetlejuice redder when it's brighter or when it's dimmer?
Okay, that depends. There's a number of things that can happen here, and I'll explain what I mean by that. If you look, and this actually takes us into the Betelgeuse discussion, and it talks about why stars are as bright as they are. But let's just go take the question at face value. Is it redder when it's brighter or when it's dimmer? The answer, I guess it's probably redder when it's actually larger and brighter. Okay, because that means that it's a larger diameter and the outer layers are farther from the core, and they're going to be lower temperature, so they're going to be redder. Temperature is going to be lower; it's going to be more red. Might not be noticeable to your eye, but it's going to be more red. As it gets dimmer, if it's getting dim because it's shrinking in size, well, then the temperature is going to increase, and that's going to reduce the redness is going to go away. It's going to go more toward the orange, and then maybe toward yellow a little, maybe. It's always going to be red. It's always a supergiant. I'm just intrigued with Betelgeuse, and for those that don't know what's going on, Betelgeuse may be going, and then holy cow, where'd it go? Or holy cow, look at that, or wow, there's a new star in the daytime sky. You've seen it before in some of the news if you've been paying attention. Betelgeuse might be on the verge of a supernova. It's something we haven't seen before. I seem to recall this kind of dimming was seen a little over 100 years ago, but it could just turn out to be a long-term cycle of Betelgeuse. But I don't know. This is acting really odd. It's been dimming really incredibly, and it's a variable star anyway, and we know that, but it's been dimming quite radically. This is sort of unprecedented. It used to have a brightness on the astronomical magnitude scale of 0.42. Now, what does that mean? Well, for reference, okay, those numbers can be positive, they can be negative. The moon, for instance, is minus 12.7 magnitude, stellar magnitude, the brightness magnitude. The sun is even brighter, so it's even more negative. Okay, the very, very brightest are negative, and the very, very faint are very positive. I know it's the opposite. Go figure. We're in astronomy. You like to just really make you work for your understanding. The sun is minus 26.7. Now, here's an easy one. In the summertime, we have the summer triangle overhead. We have the star Deneb in Cygnus. We have Vega in the constellation of Lyra. We have Altair in the constellation of Aquila the Eagle. Okay, Vega, which is almost directly overhead in August, Vega is magnitude 0.0. It is actually what we call a standard star, one we use as a standard to calibrate equipment. I use it to calibrate the spectroscope that I use for doing spectra of the stars. And I use different stars in the winter. And I use Sirius, for instance. But Sirius, okay, the brightest star in the sky, which is now rising in the east, okay, around it's already up when the sun sets, but around 10 o'clock, it's just about halfway up, maybe a little more above the horizon from the east, and Orion will be almost dead center, on your meridian. That is the halfway point between rising and setting. And Sirius, the brightest star in the sky, will be to its lower left. And Sirius, that brightest star, is minus 1.46. Remember, Betelgeuse used to be 0.42. So really almost just a little bit fainter than Vega. Remember, the more positive numbers are fainter, the negative numbers are brighter. Right? Now here's one, and this is one Daryl encouraged us to look at the other day because it was really cool. Aldebaran is in the eye of Taurus the Bull. It is the eye of Taurus the Bull. And that's magnitude 2.4. It's an orange star. It's only about 66 or 64 light years from us. So it is fairly bright in our sky. And Betelgeuse used to be far brighter than Aldebaran. And now we visually brought up Aldebaran because Daryl asked us to in Sky Tour Livestream. And we brought up Betelgeuse. And we noticed immediately that Betelgeuse was fainter than Aldebaran when it used to be far brighter. Betelgeuse used to be the 6th brightest star in the sky. Now it's 23rd. It's not even in the top 20.
I remember you saying that. I was there when you were comparing Aldebaran and Betelgeuse. Yeah, I remember you saying that. That's crazy. And in how long of a time did it drop from top 10 to bottom 20?
Well, since December of 2019 about. So,
wow.
Yeah, so it's going fast. Something's happening. Now, it's not just going to go out. That's the whole thing. Okay? And it's not collapsing. When a star collapses and goes supernova, it's a very fast event. The stellar core collapses in a quarter second. Not the whole star, but the stellar core. And then it hits the stuff in the middle and bounces off and just totally blows away the rest of the stuff on the outside of the star that's coming in at it. So and that starts a supernova event. So that'll happen fast. You'll just literally see Betelgeuse go from being an orange star in the sky to suddenly being very bright in the sky. That's what we're going to see when Betelgeuse finally goes supernova. It's not going to disappear or anything like that. So what's happening now is really odd, considering that Betelgeuse is a supergiant. Now, let's talk about this magnitude brightness a little bit more here. Now, I'll give you an idea. If you have a star that's 0 magnitude, and you go to first magnitude, okay, that first magnitude star is 2.512, that's the actual number, 2.512 times fainter than the 0 magnitude star, okay? Now, just so you can see, if you go to a 7th magnitude star, that star is 631 times fainter, all right? So now we're talking about stars that are dropping by only a couple magnitudes. So it turns out that Betelgeuse is dropping out of the top 10, and it's not even in the top 20 anymore. And so it's dropping between 6 and 15 times fainter in very short order. And that's a huge drop for a whole star the size of Jupiter's orbit. All right. So here's the question. What causes stars to dim? Well, we've talked about this before when we talked about stars. When a star forms, it has a core that gets hotter and hotter as material, hydrogen gas usually piles in. And the gravitational forces trying to crush the star will heat up the core. And the core reaches that magic temperature, okay? And when it reaches a certain magic temperature, it can then start to fuse hydrogen. All right, and then hydrogen fusion releases a lot of energy, all right? And that release of energy pushes out from the center of the star with a radiation pressure. And radiation pressure is something that fights the gravity trying to compress the star. And so a star finds its natural equilibrium of outward pressure versus inward gravitational crushing pressure. And that's where it sits most of its life. And it's called hydrostatic equilibrium. Yes, big words, but that's what it is. It reaches an equilibrium of radiation pressure pushing out and gravitational contractive forces trying to crush it. That's what happens. Now, if a star starts to run out of fusion fuel in its core, then the radiation pressure gets smaller. And now the balance is upset. Now, the star's gravity can crush it. And so the star might begin to contract. And so maybe the dimming of Betelgeuse is because it's running out of a fusion fuel that it's been using, and it's now getting smaller in diameter as it contracts. Now, the thing about that is that the luminosity, all right, and we talked about this before. We actually showed you how big Betelgeuse was on a previous Sky Tour radio. If you put Betelgeuse where the sun is, its radius takes it out almost to Jupiter's orbit. It's a massive star. Massive star. So Mercury, Venus, Earth, and Mars are completely swallowed up within Betelgeuse. And then Betelgeuse isn't even the biggest star. How about that? In the universe. So the intrinsic brightness of these stars that is called luminosity. And it's related to the radius and the temperature of the star. Okay? And it's related to the radius squared, and it's related to the fourth power of temperature. So radius squared, t to the fourth. Okay? So it's very sensitive. So if you change the temperature slightly, the luminosity changes radically. If you change the radius slightly, then the luminosity is also affected, just not as much as temperature. Okay? So when we talk about luminosity, it's always proportional to the radius of the star squared and the temperature to the fourth power. And so this is why we see radical changes in brightness of stars sometimes, because their radius is changing a little or their temperature is changing a little. So a small change in radius or temperature can make a huge difference in luminosity. Now, Betelgeuse is a red supergiant at this point, right? It's an M1, M2 spectral class, all right? However, it's a luminosity class 1A. Now, when stars are just normally fusing hydrogen into helium, they are luminosity class 5, or Roman numeral 5, or V. And that's what most stars are. We call that the main thing they do, the main sequence, okay? Well, when they run out of hydrogen fuel, they don't burn hydrogen into helium anymore. They make helium into carbon and neon and oxygen, and they leave the main sequence. They go off that line that snakes through the middle of our diagram that we have of all the normal stars that are fusing hydrogen. And they end up going off on a little evolutionary path. And one of those evolutionary paths, there's 1A, there's 1B, there's 2, there's numeral 3, there's 4, there's 5, which are the dwarfs, and then 6. Okay? So you have these Roman numerals, 1A, 1B, Roman numeral 2, 3, 4, and 5, of course, and the 6. And those luminosity classes, Betelgeuse is in a 1A luminosity class, which is the biggest supergiant. So if you recall the spectral class, the color, which Amanda said before, the OBAF-GKM, okay, that's basically the color, all right? And it gives you the temperature as well. Hot and blue are the O's, and cool and red are the M's. And the evolutionary stage is the luminosity class. So when we call our star a red giant, we're referring to its evolutionary stage. And this is what Betelgeuse is. Now, here's the interesting question. When we look at Betelgeuse now, it's a red supergiant. But what was it before? Before it was a red supergiant, it was actually on the main sequence. It was fusing hydrogen into helium. So what do we call that? What was it? Well, the interesting thing is Betelgeuse was a normal star at one point. It was fusing hydrogen into helium.
I was going to guess that. I was thinking just a normal star, but
No.
I figured it was a trick question. It couldn't be that easy.
It was that easy. It was that easy. And we're going to tell you more about that. I'm going to tell you what it was when we get back from the break. But suffice it to say that we figured this out because Betelgeuse has been doing something that is really odd. Not for a red giant, but for Betelgeuse. Okay, Betelgeuse actually has a lot of mass around it, a lot of star stuff that's been ejected from it. All right, so it's been, and we call that mass loss. These large stars sometimes will have have flares. I shouldn't say little. They'll have massive flares, and those massive flares will eject chunks of star away. Not so much chunks of star, but parts of the outer atmosphere of a star. And it doesn't have to go that fast when it's out as far as Jupiter to escape the gravity of the star. All right. And, we're going to work backwards, and I'll tell you when we get back what type of star Betelgeuse was before it became a supergiant. And again, it was only 8 to 8.5 million years ago. That's how old Betelgeuse is. So we'll be right back on Sky Tour Radio with Amanda the Great and myself right after these messages. Stay tuned.
Nancy Vernon here with Ozark Mountain Publishing, coming to you from the Ozark Mountains of Northwest Arkansas. We are a publisher of New Age, metaphysical, spiritual, nonfiction books, as well as digital downloads, DVDs, and audiobooks. This is also the home of all of Dolores Cannon's titles. The company was founded in 1992 and has been bringing to you a varied selection of titles covering many different subjects. This year, we have added a new imprint to our company, Big Sandy Press. They will be publishing titles from the genres of historical fiction and nonfiction, paranormal fiction, and more. So be sure to visit our website, ozarkmt.com, and explore all the new and exciting authors and titles coming your way.
For more information about Ozark Mountain Publishing or their events, call 800-935-0045. That's 800-935-0045, or visit their website at ozarkmt.com. That's ozarkmt.com.
Ew, yuck. They're unhealthy and gross. Bugs, I hate bugs. We keep a clean home, but occasionally bugs show up. Well, I found something that is tougher than bugs. Orange Guard. From contact, it kills bugs. Plus, Orange Guard kills hidden bugs and keeps new bugs away for weeks. I know. I use Orange Guard. Plus, all of the ingredients of Orange Guard are on the FDA generally regarded as safe list. Orange Guard may be used around food, humans, and pets. It promotes a healthier planet, and here's a bonus. Orange Guard cleans where it's sprayed. Plus, it comes with a 30-day money-back guarantee. Orange Guard.
You can get Orange Guard at Ace Hardware. And listen, folks, Orange Guard is tougher than bugs, and it's safe to use. Go to orangeguard.com. That's orangeguard.com.
Hey everybody, Rachel Ray here. Nothing brings a bigger smile to my face than cooking up a big meal for the whole family and lots of friends. But there's not enough room at my table for the 17 million kids in our country who struggle with hunger. That's why the Feeding America nationwide network of food banks collects surplus food to give hope to hungry kids. But they can't do it without your help. Support Feeding America and your local food bank at feedingamerica.org.
A message from Feeding America and the Ad Council.
The new KGRA YouTube channel is now live. Subscribe and be sure to hit the bell to stay up to date on the latest major announcements, alerts on trading topics, exclusive live streams, live video cast, and that's just the beginning. Be the first to know what's coming from the KGRA TV channel in real time. So keep it locked in to your contact for alternative talk radio on the internet. Your KGRAradio.com. Now you have the inside contact for alternative talk radio. The Planet. KGRAradio.com.
Hey, welcome back to Sky Tour Radio. It's Mark, your guide to the universe. Does that sound too pretentious, Amanda? It's kind of
all right. We know what you mean.
It's kind of weird, isn't it? It is kind of weird. Before the break, we were talking about Betelgeuse because when we talk about evolutionary stages of stars, Betelgeuse stands among the rare few that are close enough to be studied and give us a ringside seat to a process in the universe that is potentially going to change the way we view the universe. And we talked about how Betelgeuse has evolved to this red supergiant stage. It was on the main sequence, and when it was there, it was fusing what hydrogen it had into helium, and it did it rapidly. It did it so fast, in fact, that it migrated away from fusing hydrogen to helium into fusing other stuff, helium into carbon, and neon, and oxygen, and silicon, and iron, possibly at its core. And by doing so, it moves away from that narrow band we see most stars sitting on, where they have that luminosity class 5, Roman numeral 5 nomenclature assigned to them. So Betelgeuse doesn't have that anymore. Now it's a 1A supergiant. So its evolutionary stage is, well, literally, they should call it look out, I'm going to blow. I mean, that's literally what the 1A supergiant should be called. And I think that Betelgeuse will undergo something called a core collapse supernova before long, because it's going to run out of its final fuel, and then the cores are going to collapse, and like dominoes, they're all going to collapse one after the other. All the shells outside the core burning anything are going to collapse, and they're going to bounce off that core because they're all coming from all sides, and nowhere to go. More elements will be made in that mess as that collapses. But then the explosion will send material light years away from Betelgeuse. For all we know, some of the material from Betelgeuse, which is actually moving pretty quickly through space, by the way, it's actually called a runaway star. I studied runaway stars actually in getting my degree. I did a thesis on runaway stars in the galaxy, and Betelgeuse wasn't considered because Betelgeuse was a supergiant, and I was doing B stars, B-type stars only. There was just 5 or 6 of them that I found that are speeding around in this galaxy. So there's a lot of cool stuff out there. But anyway, we talked about Betelgeuse.
Is something constantly monitoring Betelgeuse at all times?
Something, a satellite or something?
Telescope, some kind of program, a satellite, I don't know, something, maybe like TESS and Explorer or something.
But I'm not plugged into all the programs, of course, but I can tell you that with the attention Betelgeuse has, I know for sure that someone's going to catch. If Betelgeuse goes, someone's going to catch it.
For sure. That's what I mean. Like, if this is like a thing we're kind of waiting for, wouldn't there be a constant feed from it? Stream to it?
Yeah, but think about it. It would have to happen from multiple observatories because the Earth's rolling around, it's spinning. So you can only watch it while it's nighttime at your place. But if your telescope was set up on Betelgeuse and, of course, the sun comes up, you can't see it anymore. So then you got to wait for the next night. And if it turns around, you come to the next night, and all of a sudden Betelgeuse is this bright star in the sky. It happened when it was on the other side of the Earth while it was nighttime for someone else, and they got to see it, and you didn't. So, but that could happen, So here's the thing. When we look at Betelgeuse and we look at the environs around it, we see that a lot of mass has been coming off of it. Now, it's actually around 20 solar masses in size, okay, 19 point, change. And it was also, it's given off a lot of mass. And so by studying the mass loss of this star, plus knowing it's about 20 solar masses, we can look back and looking at its age of 8 million, 8.5 million years old, we know that this was probably an O star. It was a bright blue star, as bright as the stars in the belt of Orion, probably as bright as Alnitak, the leftmost star, which is one of the brightest O stars in our sky. I think Daryl mentioned that yesterday, actually, in a Sky Tour live stream. I think we talked about that. And I don't. That's a little factoid I did not know about Alnitak. But see, Betelgeuse was an O star. So when we look at the upper left side of Orion and we see upper left corner of Orion, we see that beautiful red star. It used to be blue, and it used to be very bright. And it was only about about 6 million years ago, 7 million years ago, when it was that bright. So it was really, it's really changed radically, obviously, in time. Now, as an O star, we know that O stars are measured from 0 to 9, just like B0 to B9, A0 to A9. And Betelgeuse was probably kind of like Alnitak, an 09 minimum type star, based on the temperature, based on the size. And O stars have mass between 15 and 90 solar masses. Imagine a star 90 times the size of our sun, 90 times the mass of our sun. So Betelgeuse being only a few million years old and having already fused away its hydrogen in the core, only these massive powerhouse stars can do this. And that is what we're seeing here. And those are the very bright and blue O stars. Betelgeuse was probably one of the hottest stars in the universe. And here's a little thing I like to do. Betelgeuse winked into its short existence around the time that the Red Sea had just finished opening up from geological rifting here on the Earth. Okay? That's when Betelgeuse was born. Okay? That was also around the time that the southern pole saw ice for the first time on planet Earth. All right? That was around 8 to 8.5 million years ago. So, and I like looking at parallels in development that way too, So at that time, tectonic drift had created nearly the same planet we see today, right? So we'd recognize it from orbit. We'd recognize the United States. It look a little different, especially around Florida, okay? But the first primitive primates had evolved around 55 million years ago, but just after Betelgeuse was born, that's when the first gorillas appeared on Earth, all right? That's along that evolutionary sequence. When Betelgeuse was born, gorillas appeared on Earth for the first time, And because it's moving fairly quickly through the sky, we can measure it now, and it's actually moving at what we think is a swift 30 kilometers per second. Now, that's 6 astronomical units per year, and it may not seem very much, but remember that stars move for millions of years, so they will be noticeably different over time. So, and it's an interesting number, actually, because it's 6 astronomical units per year that Betelgeuse is moving. Well, we've got, we have Betelgeuse where the sun is. We know that it goes out to almost Jupiter, So I think that's pretty cool because Jupiter's at 6.2 astronomical units. So really, it means that it moves about, just about half its diameter in a year, which is pretty good if you're a star that's as big as almost Jupiter's orbit. But here's what's neat about Betelgeuse. As it's moving through space, it's actually moving through the interstellar medium, leaving a wake behind it of material that it has been shedding. And that's the other part of curiosity of these giant stars like this is mass loss. As this material reaches the far extent of the diameter of this bloated behemoth, it doesn't take much radiation pressure from a stellar flare event or whatever to push that material away permanently from the star. Now, we also know about mass loss from binary 2-star system, where the larger companion will lose mass to the smaller one as it orbits it, and these lead to type 1a supernovas, where you have a white dwarf star orbiting another bigger star, and the material comes and lands. Material moves to the barycenter, the point of the common orbital center between the two objects, and it lands on the white dwarf. And when it does, it builds up mass. And white dwarfs literally depend on being 1.44 solar masses in mass. Any more than that, and this material could cause the star to blow up and disrupt itself. And if it does, then we would have another supernova on our hand, a type 1a supernova. So this particular problem is something we've talked about before, Betelgeuse is not going to do that. Betelgeuse will be a type 2 supernova. It's going to be a core collapse where the whole core collapses and the star just goes, and you won't hear the sound, of course. But if you were inside the star's atmosphere, you'd hear the sound, because sound just travels through a medium, and out in space, it's not a dense enough medium to convey sound. But inside a star's atmosphere, there's a certain point where you actually hear sounds. I'd like to hear a sound of our star. I'd like to hear the sound of our sun. And we could, but we would probably not, the probe would not survive for long. But I'd like to hear the sound of our sun roaring. I'm sure it's deafening. So in a nutshell, that's what mass loss is when we see these unbelievably large stars. If there's a companion, they can cause another supernova. But the stars that are big like that will generally lose mass. All right. Now, in the direction that Betelgeuse is moving, it's creating what's called a bow shock. All right. Along the front, it's plowing into the interstellar medium, which isn't empty. There's other material. There's gas. There's dust, and it's plowing into that. So as it's plowing into it, it's making a bow shock. That is like a bow wave. When you look at a ship moving through water, you see it pushes the water away around the bow. And Betelgeuse is like a big blunt bow pushing material. And so we can see the bow shock, and then it leaves a tail behind it. So in a weird way, Betelgeuse is like a stellar comet, and that's sort of the term I came up with. It's not really a comet, of course, but it acts like a comet in a weird way. It's pushing material, and it's leaving material behind it as it goes. So now the question is, how did Betelgeuse evolve so quickly? It really did evolve pretty quickly, didn't it? And as an O-type star, it was really massive, 20 times the mass of the sun, based on some estimates, and based on the estimate of the mass and the evolutionary model of stars, it was, like we said, it was probably this 095, like Alnitak, the leftmost star in Orion's belt. So to the eye, as I said, it might have looked like Alnitak. All right. But, Betelgeuse literally had to fuse copious amounts of hydrogen to helium to maintain that size and mass, and fight off the gravitational pressure trying to crush it. And when those forces balance, we talked about that hydrostatic equilibrium before. But from evolutionary models, Betelgeuse probably blew through that hydrogen fuel in just about probably the 8 million years or so, plus or minus, and it became a supergiant probably only in the last 100,000 years. Okay, now it's shedding all kinds of mass, right? It's moving rapidly through space, leaving mass behind it as it goes. It's a litter bug. It's Pigpen from Peanuts, but on a grand scale. I just wanted to stop there for a second and make sure that I didn't leave any questions behind. Amanda, is there anything there that people are asking at all?
No, I think everyone's just following along.
Really? Everyone's following along?
Well, trying.
Okay, let's get into some advanced physics. No, I was kidding.
But if you guys do have any questions, definitely go to Discord, to the chat room. I'm in there watching.
Yeah, Amanda is so good with that. I tell you, I tried to start Discord today. Just to see if I could use it earlier today, and I just couldn't even find KGRA. I got it started, couldn't find it anywhere. So I don't know. I don't know what's going on there. So my little rant over it. Just want to let everybody know I'm not ignoring you. Now here's the thing: we say Betelgeuse was probably in the red giant stage, supergiant stage, for only about 100,000 years. Okay, how do we know these timelines? How do we know any star's age? Well, here's the really funny thing. The answer is we don't. But we can make educated guesses. This is why we don't say, well, Betelgeuse is going to go supernova tomorrow at 2 p.m. 2:05 if this happens. We don't have that kind of ability. We may never. Stars, the thing of it is about stars, when they're individual stars like Betelgeuse, it's really hard to age them and figure out how old they are. Unless we model their behaviors. But many stars are different. Stars like the sun will last 10 billion years. This we know from models. And so we use this data to model other stars. Plus, it's very close to us, of course, the sun, and we can model it quite well. And the sun, of course, was the first star that we actually knew very well. And so that was an important thing. Regarding, if we talk about stars like Betelgeuse that are alone, okay, well, what we can do is we can look at models of other stars that we've modeled behavior on, and we can extrapolate to stars like Betelgeuse, and regarding the age of a star like the sun. First of all, it's hard to tell the individual star's age, I said, unless it has qualities that are fairly obvious cues to its evolutionary state. Betelgeuse is actually one such star. We ask how we know its age. When the Betelgeuse become a red giant, there's telltale indicators that tell us these values within a level of uncertainty. Okay, but in general, we can make some fairly accurate assumptions. For instance, if a star is 10 times as massive as the sun, it'll have 10 times as much fuel, obviously. But not so obviously, it will use it 10,000 times faster than the sun. And less obviously than that, the lifetime is 1,000 times shorter than the sun. So that's just a rough idea. It doesn't hold for all the stars. You don't have to remember the numbers. Just understand that there are models that predict how these will operate. Okay? So, in just a rough idea, just a rough idea, but that I can tell you, okay, but these same models exist for other stars of different masses as well. For Betelgeuse, the models predict an 8 million year lifetime, and that's for a mass about 20 times of our sun. Now, since the light from a star is all that we see, whether it be radio, infrared, visible, ultraviolet, or very high energy gamma, okay, rays, we can determine much from this light. We examine the spectrum of these stars, and the spectrum, of course, is red, orange, yellow, green, blue, indigo, and violet. Right? We call that Roy G. Biv. It's a fun way to remember. Our spectrum's got a name. It's Roy. What? And of course, we can measure the infrared and the ultraviolet on each end as well. And if we see, for instance, carbon in a spectrum, then that tells us that the star is creating carbon. But we know the process by which a star creates carbon in its core. But why is the carbon on the outside? It's being transported out by something. Okay? And this transport mechanism is akin to a pot of boiling water. The outer envelope of the star is convecting. It's a convection cell, like a pot of boiling water. And this carbon that was created deep in the star comes boiling up to the surface. And that particular transportation happens during a very specific time in the life of a star. And that tells us where it is in its evolution. See? So in other words, there's qualities a star exhibits that are very, very good indicators of where it is in its evolution. And these indicators have borne fruit. We've been able to make predictions that have come true based on what we see and what we've observed and modeled. So all of what we know about a star depends on a couple of main qualities. And those qualities that you all know now are the mass and the color of the star.
We have a few questions coming in before we get too late in the show.
Okay, let's do it.
Okay, Pixie Chick wants to know, can you speak on the theoretical maximum age for a star? Very interesting question.
It is, actually, and the maximum age of a star is going to basically be among the family of stars that are the smallest and coolest. The little percolators, I've called them before, and those are the M classes, way down in the, not O's or B, A, F, G, or K, but M stars. Very, very cool. They're only about 2,500 to 3,000 Kelvin. They're sometimes called ultra cool dwarfs. These stars are the longest lived stars in the universe, and they, unlike our sun, will outlive our sun 100 times over. Our sun is going to be done in another 5 billion years. It lives about 10 billion years. It only took 4.6 billion years for us to evolve here. So, which I think is kind of cool. Well, The M class, these M-type stars down there, these ultra-cool dwarfs, literally can live trillions of years. That's trillions, okay? And that is an immense number of years. It's 1,000 times longer, at least, than other stars. That is something that I think is a very valuable understanding, because it means that the universe has long-lived stars and more planets than stars, and thus the habitability, the capability, the possibility of life existence elsewhere is actually fairly high. I think science tends to downplay the possibilities because science depends on data. I depend on data, but I speculate. I'm willing to speculate. That's just a little bit of what, I do. I will be willing to speculate, yeah. So you have others?
Yeah. Galaxy wants to know, and I think this is an interesting idea. Does our solar system ever travel through extinct solar sun trails or tails? Old trails or exhaust from the extinct suns?
That we talked about that at the top of the show. It's very possible. How do we talk about it? We didn't specifically say that explicitly. However, we did see that the Murchison meteorite showed it had 7 billion year old grains in it. 7 billion years old. Well, the solar system's only been here 4.6 billion years. Maybe that debris that coalesced into the Murchison meteorite was from exactly what Galaxy just said. An extinct or long since gone star that blew up and plunged all this material out into the interstellar medium. After all, we were made from previously ejected star stuff ourselves. Okay, so that is really important. So he could be right. Your Galaxy could be right. Any more?
Yeah, and this may have come from the Sky Tour live stream we did the other day.
Okay.
Ronald wants to know what kind of star the Crab Nebula was.
I don't know the answer to that question. We do know now that it's a pulsar, and I think it's hard after the fact. Based on the elements in the spectrum, we can determine something about the star, but I don't know if there. I mean, there might be a study out there that was sort of outside my expertise in astronomy, was to figure out the progenitor stars for supernovae. But we know that Betelgeuse was an O star before it became a supergiant. Okay, and if we just saw it as a supernova, we know it had to have a certain mass. So we know that the Crab Nebula progenitor could not have been an M star. It could not have been a small, low mass M like we're talking about. It probably wasn't a K or a G. It probably wasn't an A either, or an F or an A. It was probably an O star or maybe an early B. And because those are the ones that will go through a core collapse supernova, like we see with the Crab Nebula. But we can't specifically say what type of star it was. We just know it was probably an O, maybe an early B. By early, I mean B0, 1, 2 at the most. It depends on the mass we see, and it depends on a lot of information about the pulsar that's rapidly spinning in the middle of the supernova. So I can't tell you specifically, but I do know that it had to be an O or a B. More questions?
No, that's it for the questions.
All right.
I'm just thinking, I figure based on the, nebula or nova or something, it would be a given on what it was, but I guess there's more to it than that.
There is. Basically, the fact that it's a supernova means it had to be a certain mass right off the bat.
Mm-hmm.
Okay.
So with nebulas, like depending on the color and the shape and stuff, I would think it would kind of point to one or another. Or I don't know. I don't know enough about it, obviously, but
no, actually, you know what I like, and I'm going to say this to everybody. I really enjoyed how you've come along in astronomy. you have excelled and gone beyond. You don't just do it to pass the time. You actually learn. And you repeat things that I've said a year ago.
You're a good teacher, and so is Daryl.
Yeah, I mean,
you guys help bring it down to my level, and I think a lot of people. That's why people keep coming back. That's why people wanted it to be a 2-hour show. They crave this kind of stuff, and you display it in such a lovely way that people do learn and they want more. Well, I mean, I'm just I'm humbled by the fact that you have retained as much as you have, because you're really you're quite good. For someone that's only been in it for just a few short months to a year or two, and you don't do it every day, but so we're gonna keep an eye on Betelgeuse, and some of our Sky Tour live streams, we may just focus on Betelgeuse and watch it all night for fun. We did catch the meteor hitting the moon during the lunar eclipse, so hey, stranger things have happened. Maybe we'll catch the supernova. But until then, folks, we're going to sign off for Sky Tour Radio tonight. I hope you guys had a good time. From Amanda and I wish you adieu and have a good evening. And I'm sure if Daryl was here, he would say good night, everybody, like he always does. So good night to you, Daryl. We say it to you now. Rest well, my friend. Feel better.
And get better soon, because we missed you. And I want to thank the KGRA listening audience, the greatest audience on earth, for joining us tonight on Sky Tour Radio. We will be back next week. Until then, when you go outside, make sure you keep looking up.
Except while you're driving.